Okay, so last week we covered the first part of the geologic structures or structural geology, and this is the review portion before we dive into the second half of this. So remember last week, the reason why we care about structural geology is because, well, we live on top of the Earth, and we would like to have a good understanding of what's going on below the Earth for obvious reasons, such as landslides and such. We want to make sure that type of material that we're building on is safe and is also in a correct or optimal orientation for us to build on, and it's not prone to sliding, as we see here in this image. So we were introduced to block diagrams, which is pretty much a 3D slice of the Earth's crust, or a section of the Earth at least. And it's analogous to kind of cutting into a several layered cake, whereas we live on the very top surface, being the very top of that icing, and then when we slice down, we're able to see the individual layers and what those layers are doing, how they're interacting with each other. So the Earth is not as simple as a layered cake. It's a little bit more complicated. We have faults, and we have dikes, and we have sills. Igneous intrusions and such. All right, and last week we were introduced to folds. We were introduced to syncline synforms, anticline antiforms. So as the cartoon shows, the way to remember these is to think of syncline, as to a little what we have here, a little demon, and then anticline, the anti version of that, which would be this little angel. The way I remember it is to think of a sink and to think of the letter A. So a sink, if you take a cross section of a sink, like a sink in your bathroom or your kitchen, it creates this U structure that can hold water. So in the syncline, we have this U structure, and anticline, antiform, we have the opposite. Also, that bend forms the peak of the letter A as well. So that's how I remember those. So in this sense, what's the difference between the cline and form version? So here we have a syncline synform. So in this case, it's a syncline because we have the ages which are labeled. We know that the center part is the youngest and the outer edges are the oldest. And then likewise for the anticline, where we have the oldest in the middle and the younger layers out on the edges. We were also introduced to faults and what those do, and the labeling of the fault. So we have this diagonal fault that is going through this cartoon image here, and we label the hanging wall and the foot wall. And we know these based on if we were to imagine a tunnel, as we can see here, and a little person standing inside that tunnel, or a miner, and that miner had to hang his lantern. So he would hang his lantern on the hanging wall, so the part that overlaps the foot wall. So the foot wall is where he is standing. We had 3 different types of faults. We had our normal fault, reverse fault, and our transform faults. So our transform faults are also known as strike-slip faults, and those can be left lateral or right lateral based on the direction of movement. So normal faults, in the normal fault sense, we have the hanging wall that is moving down and the foot wall that is moving up. So this is an extensional environment, so the ground is being put under tension. In a reverse fault sense, we have a compressional environment. So the hanging wall is moving up and the foot wall is moving down. Now in our strike-slip faults, we have pretty much almost a vertical fault, and the 2 blocks are sliding side to side from one another. So there's no vertical offset. It's just a horizontal lateral offset. So the motion, the left lateral, right lateral portion, is referring to the little person that is standing on one side of the fault. If the fault were to move, we would look at the direction of the other side. So we see a line of trees there, and we see that little person. Now we look at that line of trees as if we're that person. In the left lateral sense, we could see that line of trees moving to the left. So hence left lateral. And then if you're standing on the other side of that fault, it would still be a left lateral fault. And then on the right lateral fault is exactly that same concept. We can see that line of trees moving to the right, hence right lateral. So last week we were also given these block diagrams where we had to fill in the blank. So hopefully we came to the conclusion of a non-plunging fold, and we could just draw straight lines across, like so, to show the 3D representation of what this fold would look like. Also, if we were given this in map view, we can tell that this is a anti-form, considering that we don't know the ages. So if we do know the ages and the center portion is the oldest, then this is an anti-cline. Since we don't know the ages right now, this is anti-form. So now we have 4 different layers, and we know that the beds are dipping at a very specific angle, right? And if we assume north is up, south is down, east is to the right, west is to the left, then we can complete the block diagram. So that's it for the review, and on to the second portion of the geologic structures and maps. So in this portion, we are discussing geologic maps. So if you recall the topographic maps that we looked at in the past in previous labs, topographic maps is essentially our regular map. So in a geologic map sense, topographic maps is our what's called a base map. So this is the base map, and then we overlay our geologic information on top of that. So you recall that in topographic map, we had a pretty good amount of information that was going on. We had contour lines, which gave us our elevation. We had specific symbols for buildings and roads and rivers and water sources. So if we were to add additional information on top of that, this would be our geologic information. And this is usually printed with color codes and lines and additional symbols, which would give us information in terms of strike and dip, fold types, geologic material, geologic ages. So essentially, in our geologic map, we have a lot more information being crammed onto this two-dimensional representation of the Earth's surface, essentially. So it gives information about, like I said, geologic structures, folds and faults, different types of rock information, surface geology, and sometimes subsurface geology as well. So it's all this block diagram stuff that is being projected onto the map view plane. So an example of this would be the southern tip of Africa, where we have, some additional information that's overlaid onto this gray base map, which looks like, a DEM from Google or something. So we have railroads that are being overlain on here, which is fairly important since this is a map of different types of resources. So we have D for diamonds, Cu for copper, Cr for chromium, A for asbestos. Right, so this is a bunch of new information that wasn't on an original base map that's now being overlaid on top. So another way to look at this is, our geologic maps are basically our block diagrams that are in map view. So we're looking at this on the top. So we have our initial topographic map, which is our base map, and that is shown by the street symbols that we can see that are kind of faint in the background here. And then we have our geologic information that's overlaid on top, which is all the different colors and symbols and the bold font, right? So we have QH, FP, QHB down on the lower left, and then we have KJK. So the Qs and the Ks usually refer to a specific age groups in our geologic time. Afterwards, those usually would refer to the type of rock or unit that it's being referenced to, and that's denoted by the different colors on here. We can see different symbols as well. So the 45, 35, 70, 40, 65, we can see a symbol that's right next to it, and that's our strike and dip symbol. So the number refers to the dip angle, so the degree of dip of which that unit is dipping into the earth. And then the strike symbol is the strike of that, how in line that is with the earth, essentially. We have some bold lines that would refer to fault or contact points. So some things that we would normally see on a geologic map, we would of course almost always have a north arrow. So north is usually pointed up. We would have our scale. So normally, essentially stuff that you would find normally on a topographic map, you would still find on a geologic map. We just end up with more stuff. Then we'd also have our symbols, or the legend portion of it, which would give us information in terms of the different color coding, in terms of what the geologic units are, what specific symbols would mean, if varying between mapmaker to mapmaker, if they're labeling a fault with a different unit, a fold with a different symbol, so on and so forth. Okay, so recall structures on a geologic map. Now we'll look into folds, which are repeating patterns of the geologic bed. We can see this as the zebra striking or tiger stripe pattern, where if we were to draw perpendicular to the fold axis, we would see this repeating pattern of green and blue, and this would be this repeating of synclines and anticlines, so this kind of ribboning effect of the geologic units. We would see plunging folds, so it would create this type of U shape. So depending on if it's an anticline or syncline, we would have the plunging into the page or plunging out of the page. We would have faults that are denoted by dark lines, and the fault symbols, which is this tooth patterned line. Also, our faults can be labeled with a U and D to represent the up or down motion of the hanging wall or foot wall as well. So we can see here on the bottom circle, we can see the two arrows moving in opposite directions. So this denotes that the top half of that fault, that geologic block, is moving to the left, and the bottom half is moving to the right relative to the block. Right? So this is a left lateral strike slip fault. And then on the upper right, we have this sawtooth pattern. So this is a reverse fault, as mentioned before, but this is the sawtooth pattern represents a reverse fault. So we have reverse faults on both sides. So reverse faults, remember, that those are going to be in a compressional environment. We see the dipping layer of that fault at 75 degrees. So this is in a compressional environment, so that means that wedge is being pushed up out of the page. Unconformities that represent a gap in geologic time. Remember that this usually occurs when we have an erosional event, so we're removing rocks from our geologic feature. And this is sometimes marked with the symbol as well. We can see that we have some stratigraphic units here, and we can see these clear changes between the individual layers. So in between each layer, there is a small gap of material that is missing. And that's usually how we're able to determine what material is what. So some common symbols that we would want to refer to in our lab manuals, it's going to be on page 214. This gives us the symbols for strike and dip, horizontal bed, vertical bed, so on and so forth. So this is not the same image that you'll see in your lab manual, but this is pretty similar, and it tells us exactly what we're looking for in terms of a geologic map. All right, so recall that fault symbols may vary between mapmaker to mapmaker, but usually there's almost always a legend. So always refer to the legend when you're looking at a geologic map to make sure you're looking at the right information. All right, so in here we have the U and D that's given the up or down motion of that block. And we have different symbols referring to what type of fault that we're looking at here. So we have thrust faults, we have our sense of motion, which are given by the arrows we have dip of the fault surface as well.